Let's illustrate an application of the Marcus expression for the transition state energy in the rate of charge transfer in the Avram-Ratner diode. If we take this expression down here for the reorganization energy, shown over here, and substitute a molecular size of 1 nanometer, a dielectric constant for water of 80, and a charge of 1 for a single electron transfer, lambda then turns out to be about 1 electron volt. So going to this expression for the transition state energy and using the delta G0 that we calculated from the electrochemical data of minus 1.12 electron volts in the forward direction, we see then if we take the exponential of this energy now plus the reorganization energy all squared over 4 times the reorganization energy and divide by kT, or 25 millielectron volts, we get approximately unity. In the reverse direction now, we have plus 0.112 volts, and adding this to the reorganization energy, it's squaring, dividing by 4 times the reorganization energy and kT as 25 millielectron volts, we have about 3 times 10 to the minus 20. So this illustrates the use of the Marcus theory. How does the Marcus theory correspond to reality? Well, it turns out there are significant differences in real electron transfer reactions, but let me show you a beautiful movie in which electron transfer is calculated for a chlorine atom becoming a chloride ion at a metal surface. This is a calculation in which molecular dynamics simulations were used to figure out the random fluctuations of water molecules and hence polarization fluctuations around this neutral chlorine atom shown here. This is the metal surface here, and there is an image charge of the molecules here in the metal. This calculation combined classical mechanics with quantum mechanics with a model Hamiltonian for charge transfer between the electrode and the ion, and you see there a fluctuation that's just beginning to put some charge on the atom but didn't succeed. So it fluctuated towards the transition state but didn't quite make it. This is a simulation by Mark Koper and colleagues at the University of Leiden. So you can see as the configuration gets to be about right, the charge is trying to transfer onto this atom. There it goes, and we reach the transition state, and as soon as we hit the true transition state, the ion then rattled downhill into the coordinates appropriate for the equilibrium of the product of this reaction, which is the chloride ion. So let's just summarize Marcus theory. So Cramer's theory has been adapted to get electron transfer rates. We have to introduce this concept of solvent reorganization or inner shell reorganization, which gives us an additional kinetic barrier analogous to the transition state in the Cramer's theory. The important point here is that just like in the Cramer's theory, the transition state represents a degeneracy between reactants and products. For the electron transfer problem, this is the way of getting the electron to actually make a transition under Fermi's golden rule, because at the transition state, reactants and products form a degenerate system. The fact that the transition state corresponds to a non-equilibrium state for both the reactants and the products leads to an energy barrier that will keep the system in one state or the other, i.e. it leads to charge trapping on the molecule. Note how the kinetics is dominated by the rare event of reactants and products fluctuating into a non-equilibrium configuration. So this is indeed an emergent phenomenon. And notice how many solvent molecules around an atom are involved in the process. This is indeed a transition driven by a fluctuation in a nanosystem.